Hello everyone, this edition of AHRI Insight takes a look at some of the interactions of some of our key pre-emergent herbicides. It was research led by Danica Goggin, and it picked up on some old research by Dr. Roberto Busi that we've reported on a bit in the past, but now they're trying to understand it in the lab. So we're going back to some research where Roberto Busi started with some trifluralin resistant ryegrass. He bred sort of prosulfocarb resistance, so that's arcade box of gold type herbicides, bred that resistance in the lab by recurrent selection, and what he found was as he got more resistance to prosulfocarb, the trifluralin resistance disappeared. So this research now has done a little bit more on that. They've found that it is real, it did happen. It's called negative cross resistance. That's when your resistance to one herbicide makes another herbicide more susceptible, makes plants more susceptible to that herbicide. So they confirmed that happened, but they still don't understand exactly what's going on with the enzymes in the plant. Through the research, they also had a look at where these herbicides are active. And so prosulfocarb, for example, most agronomists would know that it's more active in the shoots of the plant rather than the roots. Active in both, but the reason for it being more active in the shoots is that is where it is converted to a pro-herbicide. So prosulfocarb is a pro-herbicide. It needs to be converted into another product in the plant. A P450 comes along and makes prosulfocarb sulfoxide in the plant, and that is the herbicide, and that happens more in the shoots. Trifluralin, we know, is more active on the roots, and the reason for that is if trifluralin is going to be broken down by the plant, it gets broken down in the shoots, and that breaking down, that metabolism doesn't really happen as much in the roots. So that's why trifluralin is more active in the roots. Now the other thing that they took a look at in this research was this interaction, this cross resistance between Sakura and arcade, so pyroxasulfone and prosulfocarb. So once again, old news that there is cross resistance between these two herbicides, but the researchers, Danica and Roberto Busi and others, had a look at what's happening here. Well, what they can confirm is that it's not the GSTs. Why is that important? Well, recently we've reported that the main mechanism of Sakura resistance is the GSTs, the glutathione S-transferases. But with this cross resistance, the researchers have confirmed the cross resistance is not due to glutathione S-transferases. So what does that mean? Well, that means there might be another Sakura resistance mechanism that we haven't discovered yet. So watch this space for more information there. So what do we do with this information? Well, one is that we probably don't rotate between these herbicides. We know there's cross resistance between, say, a Sakura and arcade, or a pyroxasulfone and prosulfocarb, so we probably don't rotate between those. And the other thing we probably do is keep mixing trifluralin and prosulfocarb. If there's this negative cross resistance, then that is a good thing. The other thing to note about this negative cross resistance here is it is just metabolic resistance in metabolic trifluralin resistance we're talking about there. So that's where the negative cross resistance happens. If we have target site trifluralin resistance, which is also common, there's both types of resistance in the field, this negative cross resistance doesn't happen. So it's not going to exclusively happen. That isn't always going to happen. If you have trifluralin resistance, you can undo it. It's only going to undo it if it is metabolic resistance. All a little bit confusing, so you better take a look at AHRI Insight.